Set into
I'm at the Johns Hopkins University in Baltimore, or, to be more precise, at the Space Telescope Science Institute. At the moment, this is one of the most important places in the scientific world. It's the nerve center of the most fantastic telescope ever planned, the HST, or Hubble Space Telescope. It was named in honor of the great American astronomer Edwin Hubble. Hubble was the man who first proved that the universe is expanding and that the dim blurs we used to call spiral nebulae are in fact whole galaxies of stars racing away from us at incredible speeds. Hubble died in 1953. How could he tell that within 40 years a telescope named after him would be circling the Earth at a height of 300 miles, going once round every 95 minutes and sending back pictures better than any obtained before? The Institute is the size and complexity of a university. And among international research institutes, it's unique in being devoted entirely to one spacecraft, the Hubble Space Telescope. There are scientists who have spent all their working lives in dealing with it. Operating from above the atmosphere, the HST has perfect seeing conditions all the time, which is why, even though it has only a 94-inch mirror, it can outmatch all the larger telescopes based on the surface of the Earth. It's had a checkered history. It should have been sent up long before it actually was, but it was held up by the shuttle delays. And then finally, in April last year, it was sent into orbit from Cape Canaveral aboard the shuttle Discovery.
And liftoff of the Space Shuttle Discovery with the Hubble Space Telescope.
It was a perfect launch. As we know, there were problems ahead, but at least the telescope was safely in orbit. So let's begin with an overall view. Dr. Duccio Macchetto is head of the Science Programs Division. The Hubble telescope's always been an international project.
It was starting about 16 years ago. Previously, or earlier than that, it was entirely a US concept. And it started by having a number of people in this on this side of the ocean in the United States getting together and thinking of this big project. But as soon as it became close to being something real, NASA invited the European Space Agency to be a participant in this project. And since that time, I've been associated with it.
We all know that the shuttle delays caused the telescope to be postponed several times. Were you able to use those delays to update the equipment?
We never knew ahead of time that those delays were going to be important enough for us to go and change things significantly. But as they occurred, with particularly improved instrumentation, we had more time to do calibrations and things of that nature. We really didn't have time to change the concept in any significant way.
What were the main pre-launch problems?
Well, there were a number of technical problems of all kinds. As you build such a complex mission as the HST, there are always things that you're concerned about: thermal, mechanical, from the structure of the telescope down to the simplest of the instruments. And there was nothing really big that we were focusing on, except one thing that many scientists were very concerned about. That was the lack of system testing of the telescope, which, in a way, if we had done it at the right time, should have shown the presence of spherical aberration on the mirror.
Once the telescope was in orbit, tests began. That, of course, was the moment when it was discovered that the mirror was faulty. And it was a most unpleasant shock.
Well, you know, Patrick, we used to say that this mirror is the most finely polished mirror ever built, and that's still true. We used to say that it was the cleanest mirror ever made, and that's still true. It's simply apparently machined the wrong shape. The prescription is incorrect by about 2 microns, which in English would be about 1/50th the width of a human hair. But that small error, as minute as it is, can affect a $2 billion telescope and make the images from stars appear fuzzy.
Can anything be done about it?
There are 2 ways to get around this particular problem. One way, which we are addressing now, is to use computer algorithms, or reduction tricks, in effect, to massage the images to remove the halos. It's a process of deconvolution, the $50 word, or image enhancement. The real way to solve this problem, of course, is to get back to Hubble and to put a series of corrective lenses and mirrors on the telescope to introduce an equal but opposite amount of aberration. That we hope to do within a few years with some astronaut help on board the space shuttle.
There are 5 main instruments on the Hubble telescope. Can you tell us a bit about them?
There are 2 cameras, there are 2 spectrometers, and there's a photometer. The cameras enable us to look at the images, the morphology, the geometry, the size and structure of objects. There's a European camera, the faint object camera, and there's a US camera, the wide field and planetary camera. Both of these cameras are giving us a wide variety of very exciting information. The spectrographs, of course, the faint object spectrograph designed to work in deep space toward faint objects, and the high-resolution spectrograph enabling us to see with exquisitely rich spectral resolution enables us to split up the light into its component colors, while the photometer, the 5th instrument on board, is essentially a light meter, a very fancy light meter, I might add, and a very expensive one as well. And yet there's a 6th instrument on board that people often forget, and that's the fine guidance sensors that are used to point the telescope. They can also be used for astrometry purposes,
for
purposes of positional astronomy.
Well, it's all very exciting. Now, can you take us through some of the main results?
Sure. This is a typical globular cluster, 47 Tucani, and you can see as it exists from the ground a large ball of stars, some several 100,000 stars compacted within a few light years. These are the navigational beacons or fine guidance sensors of the Hubble Space Telescope around the perimeter of the field. Essentially, that's the best you can do from the ground. And with the Hubble Space Telescope, we can then in fact see into the hearts of these systems here, which when we blow up the interior portions into this domain here with the European or faint object camera on board Hubble, we can begin to see under high resolution conditions all of the stars that previously could not be discriminated or resolved from the ground. This is a stellar nursery in the southern hemisphere in the Large Magellanic Cloud, in particular the 30 Doradus star-forming complex. This is an image that's taken from the ground, and these are the navigational beacons or the fine guidance sensors around the field of view of Hubble. With the Hubble Space Telescope, we can look right into the core of this region. And what we've seen in raw form here, in this particular frame, with the US camera, the wide field and planetary camera, is this image here, showing a rich variety of stars deep in the heart of the system. And yet with another mode on board this camera, although this camera cannot actually zoom, we can see into the heart of yet this image, and that is what is shown here in raw form, just as we saw it on the monitors. By cleaning this image, which is an aberrated image, having much blur and fuzziness associated with each of the stars, we can then in fact see much more clearly under very high resolution, 10 times, 20 times better than it can be routinely done from the ground, into the heart of the system. Whereas previously, most of the scientific literature and textbooks would have you believe that all of this is essentially one humongous star of some 3,000 solar masses. Compared to this Hubble image, this is the best you can do from the ground.
As we know, the Hubble Space Telescope is a joint American and European project. One of the most important European elements is the FOC, or Faint Object Camera, built by the European Space Agency at Noordwijk in Holland.
It had basically 2 main roles. The first was to capture the very high resolution that we could get with the Hubble telescope, and secondly to study the sky at ultraviolet wavelengths, which have hardly been explored at all.
We all know about the fault with the mirror. Has that affected you badly?
Well, it's had some effect. Some of the programs that we were hoping to do, which include looking for planets around stars and to study the immediate environments of quasars, have been lost. Because of the aberration, as you know, it tends to spread the light out away from the point source and scatter the light out into the environments of the wings of the object. And because of that, we can't really do some of the faint object work that we were hoping to do. But nevertheless, it's turned out that other objects that we didn't expect really to be studying, we can do extremely well. And so it's sort of a swings and roundabouts. We've gained some, and of course we've lost some. One of the first results we got was on the supernova in the Large Magellanic Cloud. And when we looked at this with the telescope, we were very surprised and quite delighted to see a large shell around the supernova. This was somewhat unexpected. When we looked at the image, we were able to measure the actual diameter of the shell. And using that in combination with some other data, we've been able to get an independent measurement of the distance to the Large Magellanic Cloud, which is one of the nearest galaxies. And that's an important first step and a first calibration of the distance scale. And another image that we got fairly early on was of a very rich star field in M14. We were hunting for a nova that had gone off some time ago in there, and when we looked at the image we were completely taken by surprise. We were expecting to see a field of 4 or 5 stars, and in fact we saw hundreds of stars. And it took us a long time to realize the actual field of view. Then once we actually recognized the field, we understood the central star that we were looking for here was actually composed of several objects, and it's been difficult for us then to, we then have to really work out which of those 3 or 4 stars caused the nova. And then another nice result we got was to study a gravitational lens, which is known as the Einstein cross. This had just been resolved from the ground into 4 sub-quasar images surrounding a bright galaxy.
How does it work, actually?
Well, the galaxy acts as a lens. Of course, the galaxy is between us and the distant quasar, and acts as a lens and basically deforms the light coming from the background quasar, in this case into 4 separate images. The line of sight between us and the quasar, the galaxy is almost centered, and so in that lucky juxtaposition gives us this nice cross of objects. And then the final result that we got just a few weeks ago was to study blue stragglers in the core of 47 Tucani.
What are blue stragglers?
Well, these are very blue hot stars which are not really expected to be present in the cores of these, in many of these globular clusters. The globular cluster should have formed at a certain time and basically used all its gas and dust up in a single star formation period. However, we have found a whole lot of fairly young stars that are still burning very actively, and we really need to understand what's going on there. The important thing to realize, of course, that we just can't do this work from the ground because of the resolution of the thin object camera allows us about a 10-fold increase. And so with that sort of scale, you can really see individual stars, even in the cores of these very tight and compact clusters. And then also coupled with the ultraviolet response, where we can study blue stars very easily, which you can't do from the ground.
Of course, pointing is all important. And how do you control the movements of a vast telescope moving in free fall around the Earth at a height of 300 miles when there's nobody anywhere near it, bearing in mind that we're working in terms of fractions of an arc-second? The Space Telescope Science Institute at Baltimore is the nerve center. From there, commands go to the Goddard Space Flight Center, and it's from here that the signals actually go to the telescope. The Goddard Space Center also controls one of the most important instruments on the Hubble telescope, the high-resolution spectrograph. This is designed for studying very luminous objects in space.
It's a very large instrument. It's this upper one in here. It's about as big as a phone booth, or some people say a coffin. And the light focused by the Hubble Space Telescope is dispersed into the spectrum by optical devices called diffraction gratings, and imaged by mirrors onto detectors called digicons, which focus a beam of electrons from the photocathode onto a detector array. They're converted to electronic signals, and we get back a string of numbers here at Goddard Space Flight Center that represent the spectrum.
What are the main results so far?
I think the most exciting discovery from Hubble so far is the finding that the Lyman alpha forest is all around us. This is a name astronomers give to primordial hydrogen clouds that appear to have been left over from the earliest stage of the universe and were assumed to have dissipated by now. So they shouldn't exist, but we're finding them near our own Milky Way galaxy for the first time.
And what does that mean?
Well, what it means is these clouds are not dying away, spreading out into space like smoke rings, as we had thought. There must be a source of gravity holding them together, like some unseen kind of dark matter, or maybe a constraining medium, like a thin, hot gas pervading the universe and as yet undetected, just preventing them from expanding.
When you've got the information from Hubble, you've got to get it down here to Goddard, and that's quite a process.
That's right. Well, we have to use the tracking and data relay satellites.
Why is that?
Because Hubble is in a low Earth orbit. So it's only in view from any tracking station on the ground for a very short time, and we want to stay in as near continuous touch as possible. by using the tracking data relay satellites, we can track Hubble from above. And as it goes around the Earth, when it's out of sight of one tracking data relay satellite, we can communicate with it via another.
As we said, the data come from the telescope and are sent from Goddard back to the Space Institute here. But how is the information turned into a form with which astronomers can work?
You can see in this image here that the original data very much suffers from the effect of the spherical aberration in the primary mirror. For example, here is an image of a star, and rather than being a very sharp and a precise point of light, as a star image should be, that light is blurred out over a very large part of the image, and you can see fine structure in here and all of that. That is just an effect of the aberration of the telescope. That effect is very severe down here where we have a cluster of stars, and you can't even really discern the individual stars here because the light from each of the blurred images overlaps so much that the individual objects are obscured. However, after we apply image processing algorithms to this image, you can see now that the star up here has been isolated into the sharp object that it should be, and in this cluster of stars we can discern now the individual stars as separate objects, and this is helping the theoreticians to develop a much better understanding of the birth and evolutionary processes of stars.
So this is the way in which you take the data and turn them into something with which a scientist can work.
That's right, and we try to provide these tools that go from the blurred image to the much improved image to the scientists to use directly themselves. There are many different techniques that can be used in image processing. Some have advantages for bringing out very detailed structure, some have advantages for bringing out more large-scale structure. Now you can see in this second image of Saturn, which has been passed through these image processing algorithms, there's substantially more detail visible in surface features on the planet, and in particular you can now see very clearly the Encke division in the rings of Saturn, which is very, very hard to discern in the unprocessed image.
Part of any operation of this magnitude is the release of pictures to the public and the press. Dana Berry is in charge of the animation department, and a few months ago he made this video of the storm on Saturn.
Actually, the video consists of 60 frames, which are in turn made from 180 images that came from the Hubble Space Telescope. These 180 consist of images made in the red, the green, and the blue, and what I did was to combine each image and register them, that is to say center them within the frame, and once I did that, basically I put it out to videotape, and we have a movie.
How did you make that wonderful color picture of Mars?
Well, what we did is to take the different wavelengths of images that were made with the Hubble and basically combine them. What you see here is the different channels of Mars as they came down from the telescope. Here we have red, green, blue, and then we combine them to make a color image. The goal is to create a naturalistic image. If you could see Mars that clearly with your naked eye, that's how it would appear to you.
And now for some more spectacular pictures. As I've said, despite its imperfections, the mirror can still outmatch anything on the Earth, and the wide field and planetary camera has been showing that. Professor Jim Westphal has been looking at the results.
On the screen we see here Jupiter. This is a blue picture. You can see the red spot here. It has a dark center in it, which is a quite unusual thing through history. Notice that there's a kind of a tent-like structure in the clouds right above it, which I don't remember seeing anything quite like that. Quite unique to me, although in your years perhaps you've seen things like that before.
No, I haven't. And neither have I seen so much detail inside the red spot.
It's a striking thing. And then there's a very dark band here. It looks like perhaps an underlying cloud deck with white clouds above it, or perhaps the other way around. One doesn't know yet. Bright white clouds in this region and dark clouds here. And here you see one of the famous little white ovals that formed back in the 1930s. There are 3 of those spaced around the planet. And then here it looks like maybe we have a new little white oval forming. It has a little white cloud in the center of it here that was not there, in fact, 3 or 4 months before, when we had another picture of Jupiter just in this one color.
Well, that's the blue picture. The red's rather different.
Yes, the red is indeed different, and let me call it up here. And there it comes now. And we see a very different looking planet now. The red spot is now bright and doesn't seem to have much in the center, although from here I can see maybe a hint of a little bright area in the center that was dark in the blue picture. Notice we have some very vivid clouds up here in a region that was really not very obvious. No big dark band across near the middle, and very much structure up in the polar region here on the north, near the north polar region of the planet. And again, it's very easy to see this new little cloud forming, seems to be forming to the left here of the white oval. So the planet looks very different in different colors, and of course when we put the 3 different colors together into a color picture, that's why we see such vivid colors and greens and blues and reds and so forth, because the clouds reflect light in very different colors.
Although it's called the Wide Field and Planetary camera, it's not confined to planets. And looking way beyond the solar system, what about that superb view of Eta Carini?
Yes, it's an incredible picture, and it's, I think, one of the most spectacular pictures we've taken. It's full of all sorts of surprises. It's a star that exploded back about 1842 or 1843. The star is very near the center here, kind of buried underneath all this other structure. The star exploded and blew out all sorts of material. We used to think that it blew it out mainly in this direction, because from the ground we can see these blobs. They're just kind of fuzzy blobs. They're not something that you can really see well. And then we were able, with Space Telescope a few months ago, to take this picture. And to our utter amazement, it's clear that the thing exploded out this direction and formed all sorts of fascinating things. These streaks, which are probably high-velocity gas jets, these loop-like things, which suggest maybe there's a magnetic field involved. The shape and the bumpiness of these blobs is very, very strange business. And perhaps the most strange thing of all, this ladder-like structure at the top here, which looks like some sort of the rungs on a ladder. And it's thought to be shock waves in a plasma, in an ionized plasma, but we really don't know what those things are or what they're doing. It's very hard to tell from this. We'll be able to take pictures in 2 or 3 years that will show the motion that's occurring here by just comparing this picture with one a few years from now, and then we'll know which way things are moving.
Even though it's only been working for about 18 months, the Hubble Space Telescope is in a class of its own, one of the greatest and most ambitious scientific projects of all time. Even a few decades ago, it would have seemed like wild science fiction. And when history comes to be written, it'll be remembered not because of a fault in its mirror, but as the telescope which opened up a whole new era of discovery.